In this video, we are going to discuss something called elementary data analysis. Most of what we're doing is creating visuals to help us begin to understand the variables within a data set, but also to hopefully find some treasure and gain some insights. So what I mean by exploratory data analysis is not particularly scientific. I'm talking about the phase in the data science process where you ask lots of questions just to get to know your data and gain insight with what you're dealing with and maybe make some observations about trends and patterns within the data. In terms of what questions you should ask and how many of them you should have, that's not something that can be easily managed by a set list or a set number. What should always be true of the questions that you're asking is that they should have a meaning associated with the question. So for example, it's not generally helpful to just say, I'm going to compute the standard deviation of all of the columns. If you want to compute the standard deviation, you should be asking why you're computing that standard deviation. So a more meaningful question might be, what is the average value that I am experiencing on a particular variable, and how much should I expect those values to deviate from average? Do they deviate from average more in one direction or in the other? Those are more meaningful questions than just what's the middle or what's the standard deviation. While you might begin with a list of questions, remember that our data science process involves a cycle, and so it is very common and in fact encouraged to have questions that adapt, change, or grow over time. All in all, remember that this is a creative endeavor, and it's actually fantastic that it is so. It's going to lead us to much more beautiful and insightful answers than if we were operating according to a procedure or formula. The data that I'm going to be exploring today is the diamonds dataset. This is a dataset that's built into R via the variable name diamonds in all lowercase. And before we can dive into that dataset, we need to know a few things about diamonds. So this is our background research into things we need to know about diamonds. The main measurements that we use when assessing a diamond for its value or its price are sometimes called the 4 C's, which I've highlighted in green below. And those C's stand for clarity, color, cut, and carat. Now, carat is in essence a weight, and so the carat is going to be a continuous variable. The cut, the clarity, and the color are categorical values that come with an associated scale of best to worst. So in all of the visuals below, you're going to have your best measurement on the left and your worst measurements on the right. Now, one thing we could do to begin our exploratory data analysis is to focus on these 4 variables within the diamonds dataset and say, how many diamonds are we looking at, and how many of each of those categorical values are we experiencing? And then just to get an idea of what's going on with the carat variable, which remember is continuous, maybe we might just want to evaluate the minimum and maximum values for that. So if I take a look at carat, the minimum carat value that I have is 0.2, the maximum carat value that I have is 5.01, and then for these other categorical variables, we can perform a count on how many we have of each type, and I've chosen not to sort by the number of things that I have. We're not seeing things in descending order here because I want to point out that you don't need to memorize the scales from this slide, because with the diamonds dataset being a built-in dataset to R understands that these 3 variables, cut, color, and clarity, are categorical and has them saved as factors. So the ordering that you see here is lowest quality to highest quality, not an ordering according to how prevalent they are in the data. One thing that you might also notice is that the scale that we have for the colors that we're experiencing go D through J, which are not all possibilities that existed in this infographic. So we're really only dealing with these top 3 levels of diamond here. And similarly for clarity, we see an I1 down here. So we aren't dealing with these I2 and these I3 values. Now, one of the first things we like to study when given a new data set is the variation of a single variable. And variation, technically speaking, is the tendency of the values of a variable to change from measurement to measurement, meaning that even when we have something that has a constant value, there might be some amount of error in the way that we measure it. And so it can have the same constant value, but we might assess its value differently based on errors in measurement. For example, maybe we have a diamond that's actually a quarter carat, but one time we measure it and it's 0.24, and one time we measure it and it's 0.26. That would be variation on a single diamond, but often we like to know about the variation within all of the diamonds that we have in the data set. When we're thinking about variation, we often focus on two questions that are natural opposites of one another. The first being which values are the most common, and then we might want to think about why. And secondly, which values are uncommon, and what might those uncommon values mean? If we start with common values, I've chosen to focus on the carat variable in our data set. We might ask which values for carat are the most common and why. We might begin by taking our entire data set and creating something like a histogram for the number of carats to get a rough estimate of where most of our data lies. And we can see from the histogram on the left that most of our diamonds have a total carat level less than 2, with 1 being a pretty nice cutoff as well. So given that our data is somewhat skewed towards the lower end of this spectrum, we might want to zoom in on those diamonds with a carat value between 0 and 2 and create more bins with our histogram. And you'll notice when we do that, that we see an interesting trend with our data, which is that right when we get to those quarter carat markers, quarter carat, half carat, 3/4 of a carat, 1 carat, you see some peaks in the data that fall off rather quickly, only to peak again at the next quarter carat. This seems to indicate to us that it's very natural to measure the carat of a diamond in quarter carat values. We can also see that it's much more likely that the weight of a particular diamond is a little bit more than those quarter carat values and incredibly less likely to be less than those carat values. And this probably makes sense because of the way that people round. You're unlikely to want a diamond that's a little less than 3/4 of a carat and much more likely to want a diamond that's just a little bit more than 3/4 of a carat. It feels different somehow, and you can see that trend in the data. Another thing we often look for in variation is that second question. What kinds of unusual values might we see? And the technical term for unusual values is often an outlier. An outlier is some sort of observation that's unusual in some way. It doesn't seem to follow the trends or the patterns that apply to the rest of the data. So outliers by default, there should be a small number of them, and you should be able to describe very clearly the ways in which they're different from the others. In the example that we see here, we've taken a look at a box plot of the depth variable for our diamonds. Now what the depth variable is a combination in essence of the diamond's length and width and height, although not exactly. And what we can see from this data over here on the right is that it's very common to have a depth of a diamond in this range of about 60 to 65. That's in fact almost all of our data. And then all these little dots that are indicated in the box plot are considered technical outliers. Now it seems suspicious to me that so much of the data, all of these up here and all of these down here, would be considered outliers, but my eye is immediately drawn to these two values way down here and these two values right up here. It's also important to note that the more data we get in a visual, the more likely it is that several dots might be overlying one another, and you can see that right in here. It would be just about impossible to tell how many dots are there. And likewise, it's impossible to know if this is one observation or several, but it can't be that many, or we would have had data that skews more heavily towards the bottom. So when you find things that you view as outliers, like these two values down here, or these two values up here, it's important to investigate them further to see just how unusual they are and why. One possible explanation is that the values aren't really that unusual at all, but that we're trying to lump too many things into one category. In particular here, if we break our diamonds up according to their cut, we see significantly fewer outliers in the categories good, very good, premium. And we see more potential outliers in the fair and ideal categories, which are the most extreme values in our category. Those two specific cases may need to be investigated further for those outliers, way up here and way down here. But this certainly justifies that these values that we were seeing occurring in the middle might not be quite as unusual. So unusual values are things that we want to investigate further. If you've investigated to the extent that you're capable and you truly feel that your outliers are unusual and they shouldn't be factored in to certain instances, a really good suggestion is actually not to throw those observations away, but rather to create a new column in your data frame that's very similar to the column you're looking at, but replaces the outlier values with NA values. This ensures that you haven't truly thrown the data away and lost it forever, but using the new column with NA values in place of the original column will ensure that the outliers are not being considered when creating a particular plot or doing a particular calculation. There are other actions you could take with outlier values, including dropping them altogether, or if you feel confident that they were mistakenly entered and that you know the correct values that should be in place there, you could correct these unusual values.